As we did with the first order expression, we're going to separate our concentration terms and our time terms. So we're going to bring our concentration term over to one side, another concentration term here, and we're going to have our rate constant and our time term on the other side. And now we're going to integrate, because it is an integrated rate law. So we can integrate from the original concentration of A to the concentration of A at some time t. And then we'll also integrate from 0 time to that time t on the other side. Now I'm going to take this expression and just bring it up to the top of the page. So that's the exact same expression. Nothing has happened. And now we're going to solve that integral. So we can solve that integral. And if you want to look at these, the back of your textbook has all of these conversions if you want to look at them. So we're going to solve that integral. Now we have minus parentheses 1 over the concentration of A at some time t minus 1 over the original concentration equals minus kt. We can get rid of some of these minus signs. And so we are going to bring one original, the concentration at time t over on this side. We have our kt, and now we have this other term. The original concentration term is on the other side. And this is expressed in a certain way that gives you the equation for a straight line. And again, kinetics, you need experimental data for kinetics. And so when you measure your data, you plot your data. And so there's a lot of equations for straight lines that you have, because it's all about trying to plot data and figure out what the order of the reaction is experimentally. So here's an equation for a straight line. And we can plot this, and you can tell me what the intercept of this line is. OK, let's just take 10 more seconds. Yep. So all of you know how to analyze the equation for a straight line. So here we have 1 over the original concentration. And then our slope is equal to what here? K. So you can plot your data as your concentration of A changes with time. You can plot the data. And if it's plotted as 1 over the concentration of A versus time, and it gives you a straight line, that's consistent with it being a second order process. So in terms of second order half-life, we talked about first order half-life, and for any half-life, it's just the time it takes for half of the original material to go away. So we can rewrite this and take A to the t and substitute in the original concentration divided by 2, and then we can have t have a special name, t a half. So that's the half-life. And now we can just simplify this expression. We can bring the 2 up here, and now we can combine our concentration terms on the side. So we take 2, we bring this over, minus 1, and that simplifies 1 over the concentration of the original material here. And now we can solve for it in terms of the half-life. So the half-life for a second order process equals 1 over K times the original concentration of the material. So a second order half-life depends on the starting concentration. So that's very different from a first order half-life process where concentration term cancels out entirely. So for a first order process, the concentration of the original material does not affect the half-life, or for radioactive decay, the original number of nuclei, it's independent of how many nuclei were around at the time, But for second order process, the starting concentration does matter. So again, chemistry is experimental, and so what you would be doing in a lab, you would be trying to figure out what the order of the reaction is, and so you could try out your data. You say, I don't know if it's first or second order, so for a first order plot, you're going to be plotting the natural log of your concentrations versus time, and if second order, you plot 1 over the concentration versus time. And so you could plot your data and see that, oh, look at this. It fits a straight line really well if I plot it as 1 over the concentration. If I plot it as the natural log versus time, the data doesn't fit a straight line at all. So this is not a first order process. This is much more consistent with a second order process. So again, figuring out where something is first order or second order is done experimentally.